Great. Hello, everybody. I'm Sean MacAvaney from the University of Glasgow. Not to be too repetitive, and I'll be presenting a reproducibility study of an algorithm called PLAID. Don't worry if you don't know what this is. We'll start off by giving a quick introduction of exactly how this works. So today we'll be talking about a particular family of neural ranking models called light interaction models. This is a family of models probably most commonly attributed to Colbert. The way that these models work is basically first you take your query, encode it through a model like BERT or what have you into a set of vectors, right? So multiple vectors that kind of contextualize how each of the terms appear within the query. You do the same thing for the document, so you get kind of two sets of vectors, one per token, and then you take each of those and you compare them with one another, right? So each token in the query, you compare that with each token in the document. So you get what's called an interaction or similarity matrix out of that. So each token kind of represents the similarity between the other token in that particular context. And to score, there's a variety of methods to score this, but the simple, frustratingly simple and effective method is to just take the maximum by query and then sum those up. So that's represented here. Now, this is kind of a non-standard scoring function, so you can't really apply off-the-shelf approximate neighbor search techniques like HNSW and so on. So there's kind of been a variety of different approaches for approximating this, right, using bespoke engines particularly designed for light interaction models. One of these is called PLAID, and that's what we'll be investigating today. So the way that PLAID works is during indexing, you have your corpus, you have all your documents, you encode each of those. Remember, these are all contextualized embeddings for each token in each document. Then you perform clustering and compression of those tokens. So you essentially find a set of some tens of thousands of clusters, where each cluster kind of represents a centroid of similar vectors there, as well as kind of these residual bits that let you kind of decompress back to the original vector. So now each document is represented by a cluster ID and residual information that lets you kind of decompress back to approximately the original representation. And on top of that, as you go along, you also keep track of, for each cluster, which documents have a token that matches that cluster. Then during retrieval, you get in your query, you encode your query, and instead of comparing it against document vectors, you compare it against all the centroids. So you take each of your query vectors, multiply it by the centroid vectors, and get the similarity, yielding kind of a sorted list of centroids for each particular query vector. The way that PLAID works is then it takes the top k of those values, so it reduces that down to just the top 2 or top 4 or top 1. Which kind of gives you a very large potential candidate set of documents, right? Because remember, we can link back these clusters to the documents that they came from. From that point, there's an additional step of pruning that just basically has a value cutoff. So if any of these top k values happen to be below a score of, say, 0.5, you drop those out, which reduces the candidate set of documents a little bit more. And then there's the approximate scoring step. It's actually two separate steps, but to simplify things here, you do some level of approximate scoring of these documents, and you take the top k values of those, maybe 256, to reduce the possible candidate set even further, and then do complete full scoring using the Colbert model. Now, the PLAID original paper reported pretty good trade-offs between effectiveness and efficiency. So they're getting, as they report on a single CPU, around 200 to 400 milliseconds per query at very high universal rank. So we're seeing like 39.8 MRR at 10, which is pretty high on the MS Marco data set. In terms of reproducibility, the first question you often ask is, can we reproduce the main results of the paper? I won't spend too much time on this. The answer is basically yes. We also show that they hold on other data sets too. Obviously, we're using different hardware, so our latency measures are different. Our CPU is faster, so it's faster, but kind of the relative differences are also pretty similar. So we concluded that, yes, we can reproduce PLAID's main results. We then asked, what are the kind of interdependence between the parameters that PLAID introduces? Remember, there's these three values that kind of control how retrieval happens, the top K of the clusters, the clustering cutoff, and the approximate top K value. In the original paper, it suggested these three operational points without providing much justification of how they were chosen or how the parameters might relate to one another. You see that as you change one, you would change two of the other values as well. What we did is we performed a grid search over all of these, so using their suggested values as well as additional values, kind of extending the range of those. We also asked the authors if there's anything else worth tuning about this, and they said, no, these are really the three things to trade off efficiency and effectiveness. So after that grid search, what we do is we plot all the points, right? So here on the x-axis, we have latency in milliseconds per query on a single thread. And on the y-axis, we have NDCG on DL19, Trek Deep Learning 2019. If we take a look at the Pareto frontier, right, we obviously want to be up there in that upper left corner. So what gets us closest to that corner? That's the Pareto frontier. And we see that this the set of parameters to actually be on that frontier is really messy, right? So you change one value, then you have to change two of the others to kind of account for it, and it zigzags a little bit all the way up to the upper right. So there is some codependency of these values, as you would expect. You can't just change one without changing some other ones. And there's lots of also settings that increase latency without really improving effectiveness. So there's kind of some bad trade-offs that you can make if you don't set these properly. So how do you go about choosing the parameters for PLAID? Well, what we do is we now kind of link together these parameter sets. So in this particular figure here, what we do is we fix two of the three parameters and we vary the last one. So the red dot here is top K of 256. With all the rest of the parameters the same, that links up to the next point and the next point and the next point. So what we see, the approximate top K value, this is kind of that last stage, how many values are you going to score exactly. We basically see that there's no reason to set that value below 1024. It increases latency a bit, but it increases effectiveness a whole lot. So unless you're willing to trade off the effectiveness of your engine a lot, you really want to set that at least to 1024. There's probably even better values in between if you wanted to grid search a bit further. So there's no point in setting that particularly low. And there's also no reason to set it too high, right? Once you reach a certain point, you actually find all the documents that you'll probably ever get and that you need to match, and it flatlines at the top there as well. So that's this approximate top K parameter. How about the other ones? The cluster top K, so this is the first stage, how many clusters you're matching per token. Here we actually see some reasonable trade-offs, right? You see each of these kind of having a curve. You trade off some latency for some effectiveness. However, the best trade-offs are when you're already doing pretty well, right? So you kind of already have to set the parameters, the other parameters as well to get good trade-offs with top K. And the last parameter is the cluster cutoff value. So this is the manual cutoff score where you kind of prune off additional values there. It's generally good to pick a higher cutoff, but the best value is sometimes inconsistent. So this one is a particularly hard value to tune, as we found. Right, so selecting Pareto optimal parameters is actually challenging. There's some codependence between them to keep in mind. The easiest way to improve results while balancing efficiency is basically just to increase that approximate top K value. So that final one where you choose how many you're going to score exactly. And when we think about what that's actually doing, right, we're going from the entire collection, having a pool of documents and slowly narrowing it down. What we're doing is essentially we're making this last step as large as possible. So what we want is we want a large set of documents with pretty high recall for that final bit. Which kind of begs the question, right? Like we actually have a lot of good methods for producing a good large set of candidate documents. So that brings us to the third question. So how well does PLAID compare with existing lexical re-ranking techniques? So here we have the PLAID pipeline that we were looking at before. An alternative approach would be just to simply re-rank the results. So you could use BM25 with an efficient retriever like PISA, as we used in the paper, and take the top K results of that and then do exact scoring based on that. So this is a kind of simple baseline that we thought was pretty reasonable to include. So when we compare that, we have the BM25 re-ranking here on the left, and PLAID slightly over on the right, what we see is that, at least in the low latency settings, re-ranking is actually pretty optimal. So what you get is you get, for instance, 7% better NDCG at the same latency, or 41% faster at the same NDCG, again, depending on the exact points that you're looking for. This kind of surprised us. So why does that lexical matching work so well here, right? If you're trying to approximate this, complicated late interaction model, why is just matching on the tokens doing particularly well? So we dug into the actual cluster centroids and looked at the particular tokens that they originally came from. So for instance, we have this cluster number 4169 that talks about growing and grows and growing and so forth, right? So most of the tokens that match this particular cluster are basically just something you could do with a star, right? So you have all these mechanisms to do the cluster matching, but ultimately it just comes down to matching individual tokens. Of course, that's not always the case, right? So cluster 22,500, whatever. This is matching CLS tokens and subtokens and stuff like that, and kind of doing more semantic matching. So of course, it's not always exclusively doing lexical matching, but a lot of the time it is. And in fact, the vast majority of clusters match predominantly just a single token. More details on these experiments in the paper, in this analysis in the paper. Now, when we're ranking, it doesn't reach the exhaustive effectiveness when you're dealing with some medium amount of latency, right? So in a range of 150 to 300 milliseconds, PLAID is actually doing much better. So if you're looking to get higher effectiveness, you might want to do that. Last year at SIGIR, we introduced a slight variation of re-ranking called ladder. And the idea here is to introduce a little feedback loop as you're re-ranking, where you take the top scoring documents, you look up their neighbors, and you also score those. And you kind of iterate on that process to continue to find matching documents. And when we look at ladder as well on this frontier, we see that that technique kind of completely eclipses both re-ranking and PLAID there. So it's kind of completely optimal, at least on data sets with extensive annotations like Trek Deep Learning 2019. It's worth noting that it's not always a strong approximation of full retrieval. For instance, we can instead of measuring the the final effectiveness, what we could do is we can measure how similar the results are with an exhaustive search over the entire corpus using your late interaction model, and then see how close of an approximation that is. Unsurprisingly, I think we found that PLAID is actually providing a very good approximation of scoring the entire corpus. So if that's more of what you're looking for, if you kind of have a lot of faith in your late interaction model and you want to try to approximate that as close as possible, it's worth doing something like PLAID because it's kind of more directly applying what a late interaction model does. Quick summary. We were able to reproduce the main results of PLAID, the PLAID engine for late interaction models. We provided a set of recommendations on setting PLAID's parameters, both particularly in terms of the top K values of the other parameters and how they interact with one another. For low latency retrieval, we found that re-ranking and ladder are super competitive. So if you are looking for super low latency, it's really hard to beat something like re-ranking. And if you're willing to put up kind of additional cost in building up a proximity graph of documents ahead of time too, that can be even better. We provided some analysis showing that PLAID's clusters are largely perform lexical matching. So a lot of what it's doing in cluster matching is just what a stemmer does, although not completely. And the final core lesson that I want you guys to take away from this is just to be careful about weak efficiency baselines. There's a lot of talk in the community about weak effectiveness baselines, but also when doing efficiency work, do consider strong efficiency baselines, for which re-ranking is frustratingly difficult to beat. All right, thank you all, and any questions?